And depending on when your flight leaves, getting up at 3 in the morning to drive down to catch an early flight is also kind of miserable. So if you get if you can afford a hotel room and they let you keep your car there, and then you can just kind of hook up and do that, it can be helpful. So.
I'm sorry, y'all. My mom wanted to say hi.
Oh!
I forgot you're in class.
Hello. How are you today?
I'm good.
Are you enjoying the snow?
No, I get to enjoy it because I get to leave it.
Yeah, it's kind of hanging out here for a bit, so.
It's nice. Okay, sorry to interrupt.
No problem.
Sorry about that.
No, I like a cameo like that. That's awesome. All right. Well, enough about snow and cold. Let's get started on stuff. Questions about this problem set. Things that have come up. Okay, one thing, Brittany asked a question. It was a good question. So to be clear for this first problem set, in your hand calculations, want to see your hand calculations for your Bayes factor and your S values, so you can go ahead and you're creating that Excel sheet. For sure, use that to check your values and things along those lines. But for this first set, just go through. I want to see that you sort of understand how to crank these out by hand. So just don't default to your calculator for these this go around. Does that make some sense? Okay. And then as we move forward, because as you might be noticing as you're working on this, depending on what value you put in for to calculate those S values and those Bayes factor, not the S values so much, those generally turn out to be pretty consistent, but your Bayes factor can start to jump around quite a bit depending on if you're plugging in a T statistic or a P value or things along those lines. So just be, as we move forward, just remember to tell me exactly sort of what you use to calculate sort of whatever you did, but we'll talk about that sort of when we get down the road. Okay. Any questions about that set? Okay, cool. All right. Other thing too, just to, in terms of thinking about scheduling moving forward, we're going to go ahead, in the midst of COVID, for sure, we're going to cut the semester exam. So you don't, what's CJ grinning over there for? Do you have thoughts about that?
Sounds great, Josh.
You guys didn't have to take one for you didn't have to take did you take a midterm for 5300?
Yeah, we took the first semester midterm.
No, for 5300.
Oh, this is 5060. No.
Yeah, see there, so stop smirking like these guys are getting off. So, yeah, I don't know. I think you all are picking this stuff up really well. We'll go through, just drop that. As long as everybody's comfortable with this, I mean, it then makes all of your grade dependent on problem sets, but you all are doing really strong with this stuff. Things are looking really good. So if people are comfortable with that, I think I would rather, we're a little behind, but I would rather go through, make sure that we're just sort of working on sort of this stuff. So give me a thumbs up if this sounds good to everybody. Okay. Robert was slow. I was like, Robert, we got one abstention, so I guess next week, right? the day after election is when we'll have our midterms. So we'll go through, cut that. So don't worry about that. Cut that off your schedule. We'll just continue to go through and hopefully be in a good place by the time we hit the end of it. Okay. All right. So let's open up and start talking about then power and confidence intervals for our effect sizes. Okay. So just general overview. We're going to talk a little bit about power, factors that influence the power of our tests, getting into some issues of non-centrality parameters, calculations of power. Then we're going to get into some confidence intervals for our around our effect sizes. Okay. We'll say that this is an area, at least for psychological sciences, that's continuing to develop. We're starting to see not only effect sizes are starting to become more and more common, and in our sort of top ranked journals, they will require you to have them. Confidence intervals or effect size kind of take this to a whole nother level, and it's controversial in some ways, but I think a good thing to know how to do and interpret, and sort of helps again give us a stronger understanding of what our data can and can't say in terms of things. So here so I can see everybody at once. All right. Cool. All right. So, real quick, wanted to revisit this idea of experiment or error. Remember that we've got two types of error that we generally talk about within our statistical test. Our type 1 error, this is made when we reject the null hypothesis when the null hypothesis is in fact true. Okay, there's no difference between group A and B. X and Y are unrelated to one another, but we make a mistake and claim evidence or claim evidence against the null hypothesis when in fact the null hypothesis is true. Essentially what we're doing here is we're claiming an effect when there is no effect actually in the state of nature. Okay. Type 2 error, this is the opposite. This is where there is an effect. A and B are different. What's that? Yeah. Oh, yep, there we go. Thank you, Ari. You back in, Brittany?
Yeah.
Okay.
My program just shut. You know how Zoom does.
Oh, no worries, no worries. It tried to ban you to the desert, to outcast. All right, cool. So, getting back into this. So, type 2 error. This is where we fail to reject the null, right? We say that we don't have sufficient evidence to reject the null, but in fact, A and B are different. There is a relation between X and Y, and this is going to be our type 2 error, okay? And so when we're going through, what we generally are worried about is controlling our type 1 error. And what do we set? What is it that we set to control our type 1 error in our statistical tests? As we're going through and running our tests, what determines the amount of type 1 error we're willing to tolerate? What do you think? Oh, Allie? Yep, alpha level, exactly, right? And so we don't sometimes we forget that we set this because just industry standard is alpha equal 0.05, right? But there are situations where we may make an argument for more stringent alpha, or perhaps maybe loosening it up a little bit, right? Hard to get away with that, but there are cases where that might be the case, right? But we're typically less concerned when we're thinking about planning studies and thinking about interpreting things as the possibility of a type 2 error, okay? This idea that we might not claim evidence, that we might miss an effect, we tend to be less concerned about this, right? And why, Robert, why might this be problematic? Why should we probably be paying more attention to type 2 errors?
Because type 2 errors are concerned with like the generalizability of the study. So in other words, if we don't have a high type 2 error, then wait, am I getting that mixed up? No.
Well, I think you're sort of circling the landing strip here, right? So thinking about, I wouldn't say generalizability, I would say interpretability. So what can we actually draw from the study? Someone help him out. What Natalie, why might we want to sort of maybe think more about type 2 errors than the impact of type 2 errors?
Sorry, you said why do we want to think about type 2 instead
Yeah.
of type 1?
Well, or why should we think about type 2 in addition to type 1 errors?
So I guess if we fail to reject something that we should have rejected, it could be have harsher implications than rejecting something, or than rejecting something we shouldn't have. Did that make sense?
Yeah. So, and it certainly depends on the situation, depends on the study, right? But essentially, what we're doing with this type 2 error is we're missing effects that are there, right? We're saying that we don't have evidence for an effect when an effect in fact exists, right? And so, depending on the situation, that might be kind of a serious thing, right? If we say, oh, hey, sort of this thing doesn't work for treating COVID, but when in fact it does treat COVID, then that's kind of a big miss, right? And, so this historically, our concern with type 1 error, a number of different things that go into it is part of the inherent structure of our null hypothesis testing, right? Our null hypothesis testing, we don't want to give, we won't want anyone to get a free lunch, right? We don't want you to go through, I don't want Riley claiming evidence for an effect if there's no effect there, right? And so I tend to be more concerned about this type 1 error, and our hypotheses tests are set up to try and minimize, remember in that alpha, so to try to minimize that. So it's sort of part and parcel of our type 1 error, whereas type 2 error, that doesn't get built in so much, at least in terms of the explicit structure. Historically, type 2 errors have been very difficult to calculate and to estimate, and so if things are hard, people are less likely to do them. Now with the advent of technologies and computers and things like that, it's started to become more commonplace. But historically, it's been a difficult thing. I'm using a lot of tables that are not terribly complete. Other thing that I think happens is our awareness of type 2 error makes us sad and unhappy. Okay. Our studies in psychological science are hugely underpowered for the most part, right? And if I have an underpowered study, Rachel, what limitations do I run up against with an underpowered study?
It's harder to detect an effect.
Yeah, right. And if I fail to reject the null, Rachel, if I come up and I fail to reject the null, what can I say about sort of whatever question it is that I'm asking?
Not a whole lot.
Yeah, exactly. Basically nothing. Results are ambiguous. I can't say that there is effect. I also can't say that there isn't, right? At least if a null test told us that there was a zero effect, that would be one thing, but it doesn't. It just says we don't know much about anything, right? And so when we come up with an underpowered test and we find null effects, that doesn't mean that the effect isn't there, that X and Y aren't related, or that A and B aren't different from one another. It just says that we don't have enough evidence to say that there are, right? And if we went into a lot of our studies sort of recognizing the fact that sort of our opportunity to identify an effect, if it is there, is essentially a coin flip, that starts to make us dispirited and sad. And so it's easier to just ignore it and pretend that it's not an issue, right? So this has an issue when we're talking about these type 2 errors. We're essentially talking about power, okay? And think about power as the long-term probability of rejecting the null given a study with a particular effect size, alpha level, and sample size, okay? So if I were to repeat this study over and over and over and over again with the same population effect that I'm looking for, the same alpha level and the same sample size, how often am I going to reject the null, okay? And when we're thinking about these power analyses, when these are used most appropriately is when we're trying to determine the expected power of some study before we conduct it, okay? So before we start collecting data, what we should be doing is saying, okay, how many people will I need to adequately power this study given the assumed effect that I'm trying to detect, okay? Or maybe we go through and we need to use this. Again, we can do this a couple of different ways. One, I can say, so Robert's running a study, said I can collect 100 people. I have the resources to collect 100 people. Given the effect that I'm targeting, what's the power of this study going to be if I collect 100 people? Or on the opposite hand, say Allie's doing a study and Allie has infinite resources, and Allie can just say, how many people do I need to adequately power this study? And maybe it's not 100, maybe it's 300. And so Allie says, okay, I'm going to collect 300 people, right? But the idea is this is all happening before you start data collection, right? This is when we're using our power analyses appropriately. Okay, but the tricky thing with our power analyses is that it's not an exact science. Okay, generally what we're trying to do with our power analyses is trying to get some estimate of whether or not I'm closer to power 0.8 or power 0.3. Okay, this is much more horseshoes than precision science. All right, any ideas on why? What's the thing that complicates a priori power analyses? If anybody's for anybody who's sort of done one of these before.
Isn't it the fact that, like, well, what I'm thinking of is like the G power thing. I had to do it. Is that right? Like, you're just estimating your effect size. You don't have.
Yeah.
Is that it?
Yeah. That's it. In some cases, if I'm looking for an effect between X and Y, right, and I have some meta-analyses where I've got a bunch of studies that have used the same measure that I'm wanting to look at, used the same methods that I want to look at, and have all kind of targeted in on a specific sort of an aggregate estimate of effect, then I've got a pretty good idea on what I'm looking for, right? But most of the studies that we're looking at, and if I had to go through and if we sort of jumped into the future and saw all of your theses, probably you're asking a question that either not many people have asked, because if a bunch of people have asked it, then it's not super interesting, or you're using a method or measures or some type of population where there's not a lot of good background information on, right? And so what ends up happening is we have to go through and find some guesstimate of what type of effect we're looking for. Are we searching for a small effect, a medium effect, a large effect, right? And if we go through and we look at thinking about what we know about publication bias, those studies that are that have been published, are they likely to overestimate or underestimate the actual true population effect? What do you think, Erica?
They overestimate.
Yeah, there we go, right? Because if the effect that I'm actually looking at, if my population effect is, say, D equals 0.2, right? But I just happen to collect a sample where my observed effect size in this study is D equals 0.8, right? I've wildly overestimated, my sample wildly overestimates the population effect. But if I got a large sample size or a large effect size, I'm probably more likely to have found something that falls below P equal 0.05 and more likely to publish, right? And so, Erica, you don't know this. You publish the effect and say, yeah, I think my effect size is about 0.8, when in fact it's 0.2. And so that way, when Natalie or I or Ari or Rachel, other people are going through trying to power their study to 0.8, because yours is the only study that's published that's out there, we're all wildly overestimating the effect that we're chasing and not getting enough people, and so we're failing to find an effect, and so then none of our stuff gets published. So yours is the only mark out there, right? And so the idea is what we want to try and do is try and find and get a good assessment of sort of what this effect size is that we're chasing, and then trying to get it close to sort of power equals 0.08. Okay. 0.80. 0.80 is kind of the accepted standard for an adequately powered study. It's semi-arbitrary, but the idea is that if I have a study that's powered, that's underpowered, or power is less than 0.80, we'd say that there's an unacceptable risk of type 2 error. Okay, I'm going to run this study, but I'm not going to find anything. But I don't know if I'm not finding anything because there's nothing out there to find, or because I just don't have enough enough people in my study to go through and identify the effect. Okay, power greater than 0.80. Some arguments that sort of Allie, with her infinite number of resources, right? She only needs 100 people for her study, but she collects 500. Not a good use of resources. Also, some concern about unwarranted conclusions, right? If you want to make sure that you find whatever your evidence for whatever your hypothesis is, just collect 1,000 people, right? And then all of a sudden, those correlations of 0.1 and below start to become significant, right? They are associated with p-values less than 0.05, but we don't know if that's sort of anything meaningful, or we could argue, is this anything meaningful, or is it just evidence that sort of the actual relation between x and y isn't exactly zero? But that's generally not an interesting hypothesis, and we know that that's theoretically false always anyway, right? So just thinking about when we're going through empowering studies, wanting to get somewhere in that 0.8 is sort of what we typically talk about in terms of convention. Questions about power? All right. So power is a hard thing to think about, and it's a hard thing to wrap your head around. Has anybody sort of done stuff with power, or sort of had to sort of deal with this stuff in previous research labs or anything like that? Okay, a couple different ways we can think about power. Okay, so for our PSYC folks out here, think about like an example using stereotype threat as an example. Here, what we've got is we've got a sample of white men coming in to perform some math task, right? And we split them into two different groups. Control group, they just come in and they complete their math exam. Threat group comes in and we tell them before they complete their math exam, we say, oh, hey, here's this math exam. Sort of Asian students typically perform better on this math exam than white students do, okay? Go ahead and go through and take it, right? And so the idea underlying stereotype threat is that this triggers a stereotype and should then subsequently impact performance on this task, okay? And so let's say that we have two different groups. We've got 20 people in my control group, 20 people in my threat group, right? And I know, let's say for the purpose of an example, that I know mean performance for individuals who come in without any type of stereotype threat have a mean of 9.64 and a standard deviation of 3.17. Individuals in the threat group, and this is a population effect, so we're saying that we know this, score a mean of 6.58 in the population and a standard deviation of 3.03. Okay? So what we would do if we want to know the power of a test of sample size 20, okay? What we would do is we would randomly select 20 observations from a population of scores with a mean of 9.64, standard deviation of 3.17, okay? I'm randomly selecting a group of 20 scores from a distribution that has these characteristics here, okay? Then I'm going to take another random 20 observations, randomly pull those from a distribution that has a mean of 6.58 and a standard deviation of 3.03, okay? Now, Riley, in this sample of 20 observations, is my sample mean going to be exactly 9.64 with a standard deviation of 3.17?
No.
Nope. It's going to vary around a lot, right? I've got a distribution of scores, right, that I'm pulling 20 observations from, and the distribution of scores, the population has a mean of 9.64 and a standard deviation of 3.17, but the 20 people that I get are going to have some different mean and standard deviation. Same thing with our 20 observations that we pull from the threat population. That distribution has a mean of 6.58, standard deviation of 3.03, but my 20 scores that I pull from that are going to have some values that are sort of slightly different, okay? Well, what I do is for my study, and thinking about this is kind of what we're doing with our studies, right? We're pulling 20 observations from a population that has this characteristic, 20 observations from a different population that has some different characteristics. What we're going to do is we're going to calculate our test statistic and record for the difference in means, right? We're going to calculate a t-test based on my two groups that I've done, and then I'm going to do this 1,000 more times, okay? And if I do that, and then I plot out the distribution of my test statistics, okay? So this distribution is my t-value for 1,000 replications, randomly pulling samples of size 20 from a population with this characteristic and this characteristic, okay? And if I do that, and plot this out, I'm going to get a nice distribution of t-scores, right? And what I'm going to do is I'm going to look for how many t-values fall at or beyond 2.024, okay? Where did I get 2.024 from? What do you think, Natalie?
Is that in terms of like or Z values, like Z-scores?
Okay, close. Not Z's, but so here we're using test statistics, right? Because we're calculating from samples. So where did I get that? Where does 2.042 come from?
Did it come from the table?
Yeah, it comes from my table. If I go through, or if I go to my critical t value, right? So I've got 20 in one group and 20 in the other group, right? So my degrees of freedom are 38 for this test. If I go 38 degrees of freedom, critical value for a t-test at 38 degrees of freedom at 0.05 is 2.042, okay? And so what I do, over 1,000 replications, I have 1,000 different t-statistics for each one of these studies, right? And what I'm going to do is I'm going to go through and look at how many or what percentage of those t-statistics exceed a value of 2.042, right? Because some of these studies are going to have very high t values. Some of them are going to have low t statistics, right? But what I'm interested in is how many of those t statistics over that 1,000 replications are going to fall above my critical value, okay? Because these test statistics, if I get a test statistic that falls above my critical value, Ari, what decision am I going to make on that for that study, for that individual study? Yeah. So if I get a test statistic on any individual study that exceeds 2.024, what decision am I going to make in terms of reject the null or fail to reject the null? Reject the null, right? So those are the studies that I'm going to identify and sort of claim evidence for an effect. Those studies that have t statistics that are below 2.024, those are the studies that I'm going to fail to reject, okay? And so there is a real difference between these two populations means. They're not identical, right? So in this graph, Brittany, what portion of this graph am I seeing my type 2 errors?
One second. Failed to, if it is the white part, the below part?
Yep.
Yeah, the white part, right?
These are my type 2 errors, right? These groups are different. They're not the same, right? But for this proportion of my tests, I failed to reject the null, right? I've made a type 2 error on these. This blue shaded part, this is my power. These are cases where I've rejected the null hypotheses when I should, in fact, reject the null hypotheses because these two means aren't equal with one another, okay? So what I can do, if we think about this, is thinking about if I were to replicate this study an infinite number of times, assuming that there is a true population difference, what percentage of those studies are going to go through and reject the null hypotheses, and which one of those are going to fail to reject? The fail to reject, these are my type 2 errors, okay? And so if I look at this distribution of t statistics, I'm seeing that 86% of my values fall beyond at or greater than 2.024, and this is going to represent my power, okay? So again, if I'm thinking about power as the long-term probability of rejecting the null hypotheses given a specific effect size, alpha, and sample size, this is what's going on here, okay? People kind of see how this is working out and sort of a kind of a conceptual definition of power. Okay. We good? Okay. Another way to think about this, Okay, so to separate examples. So this is kind of a replication conceptualization of power. We can also think about power in terms of overlapping distributions. Okay, in this figure here, we've got two sampling distributions, right? I've got the sampling distribution here, HO. This is the sampling distribution when the null hypothesis is true. Okay. I've also got this alternate distribution, H1. This is the sampling distribution when, and this shouldn't be HO, this should be H1. CJ?
Yep.
Can you email me and remind me to change this slide?
Yep, sounds good.
Cool, thanks. So this H1 distribution, this is the sampling distribution of the mean when my null hypothesis is false, when population 1 doesn't meet population 2, okay? But the placement of this alternate distribution is based entirely on the extent to which these two distributions are different from one another, okay? So if I look at this is the distribution I would expect if the null hypothesis is true, right? This is the true state of affairs in terms of sampling distribution here, okay? And so if I look at this, okay, my heavily shaded area in my null distribution. So if I'm looking at the null distribution right here, this is my alpha level, okay? And remember, think of what we're going through when we're doing those initial tests, right? We said, okay, here's our alpha level, here's the cut point. If we find things that are falling outside, we're going to fail to reject the null. Here's my alpha, right? But if I look at where my alpha is set up, area in my alternate distribution to the left of alpha is my type 1 errors, okay? So here is my hypothetical distribution, right? Here's the actual distribution in real life, right? But if I find a score for H1 that is exactly the population mean, right? Does this mean right here, does this fall beyond my alpha level on my overlapping distribution? Nope, right? So if I get a score of 1, right? And let's say my alpha is set up at, say, 1.5. If I have a test statistic of 1 doesn't exceed 1.5. And so what's the decision I make here, Erica?
Reject, right? Wait, sorry, what was your
Oh,
clinical?
yep. So if this is the value that I actually obtain, right? Based on my null distribution, do I reject or fail to reject?
You failed to reject.
I fail to reject, right? Now, is the mean value of this distribution equal to what I'm assuming under the null? Erica?
No.
No, it's not, right? So what have I done here then in this test? What type of error have I made?
Type 2.
A type 2 error, right? So even though the null hypothesis is false, right? The distribution of whatever mean I'm looking at is not the same as what's assumed under the null. It's just not over enough. Even if I have perfectly estimated the mean of this distribution, it's not far enough off the null distribution for me to claim evidence of to reject the null. Okay, but what happens? Again, Erica, help me out. What happens if I get a value or an estimate for my alternate distribution that falls out here? Now what do I do?
You reject.
Then I would reject, right? And this outside this white, sort of this portion of the distribution here, this represents my power, okay? Now, what's tricky about this is if I find a value out here, Rachel, have I done a good job of estimating my population mean?
No.
No, I haven't, right? I've overestimated my population mean, right? But I've overestimated enough to reject the null hypothesis, right? So even though I don't have a good estimate of my population mean, I caught something on the end of this distribution that was enough for me to go through and reject, right? And so we start to see is that if we have, so in this situation, right, my assumed mean under the null is 80, but my actual population mean is 86, right? But still, even with this, even though they're not the same, the null hypothesis is false, right? But the majority of tests that I'm going to make out of this, I'm going to fail to reject the null, right? But let's say we take a different example here, and let's say our means are different. So my assumed value under the null is still 80, but my population mean is actually 90. Okay, Robert, what has this done to my risk of type 1 error? Or excuse me, my risk of type 2 error in this second scenario?
So I'm trying to read my notes. It increases the probability of a type 2 error.
Increases? So if the shaded area to the left of the distribution is my type 2 error, is my type 2 error greater or less in this second figure here?
Decreases.
It decreases, right? Because now, right, Rachel had told us in this figure, right, if I go through and I get a score on the high end of the distribution, I have a poor estimate of my population mean, but I avoid making a type 2 error, right? Down here, if I perfectly estimate my population mean, Rachel, what's the decision I make in this scenario?
Sorry, I'm confused with what the question is.
Yeah. So in this scenario, let's say, so I go through and I find my sample perfectly estimates my population mean, right? If my null, if my null hypothesis is a population that the mean is actually equal to 80, and I find a mean of 90, do I reject or fail to reject here? In this second figure.
Would you reject?
Yeah, I would reject the null, right? Because this value falls in my critical region set under the null hypothesis, okay? So what we can think about in terms of power, right? If we're thinking about power being determined by alpha, population effect, and sample size, right? What's the difference between this scenario and this scenario here? Allie, what's changed?
The difference between your null and alternative, or like the two sampling distributions.
Yeah, and what does that map onto? What do we call that? Or what does that reflect?
Wait. Sorry, what?
Okay. So here we've got this much distance between my overlapping distributions. In the second one, we've got this much difference between my overlapping distributions. What's changed in these two scenarios?
I mean the type 2 error.
Mm-hmm.
Is that what you're asking? Like
Right. But if power is determined by alpha, effect size, and sample size, what changed across these two scenarios?
Sample size.
What do we call the difference between what do we call the absolute magnitude of an effect in the population?
Oh, the effect size?
The effect size, right? The effect size has changed from here to here, okay? The true population effect here is, if we're just identifying it as a difference, we have an effect size of 6, if we're just going on raw difference. Here, the effect size is 10, right? So even if we have the exact same number of people in this scenario, as opposed to this scenario, what we've done by increasing the effect size, we decrease our likelihood of our type 2 error, and we've increased our power across these two examples, even if we keep everything else being equal, okay? So thinking about as my efforts of as my study starts to, I'm trying to detect a smaller and smaller and smaller effect. Brittany, what happens to those as my effect gets smaller and smaller? What happens in my overlapping distributions?
They overlap more.
They get more and more overlapped, right? And it starts to become harder and harder to detect that effect. Okay. $1,000 bonus question. How do we get these sampling distributions to start shrink up? So even if I have a very small effect, that overlap starts to decrease. What can I do?
Are you asking anybody or me?
Yeah, anybody.
Could you repeat the question?
Yeah.
Thank you.
So let's say that I'm looking for an effect that's sort of very, very small, right? And so my problem is the greater extent my sampling distributions are overlapped, the harder it becomes to test to find that effect, right? But how do I go through and start to shrink up those sampling distributions? What do I call the variability of a sampling distribution? What's that called?
Standard error.
Yes! Big high fives. Yeah. It's a variability of our sampling distribution is just our standard error, right? And Erica, how do we shrink up standard error?
Increase sample size.
Increase our sample size. So up here in this distribution, right, we've got a smaller effect, right? But if I start to increase the sample, let's say I have samples of size 20, right? But let's say I bump that up to samples of size 100, right? What happens to the variability of that sampling distribution? It shrinks up, right? And if the sampling distribution shrinks up, what happens to the overlap in these distributions? Starts to become sort of less, and sort of basically at probably 100, they'd be separate from one another, right? There's no overlap, right? And so thinking about power in a couple of different ways, we can think about this as the long-term probability of rejecting the null over replications, and this starts to become a nice way to think about things in terms of overlapping samples, right? So if I can go through and either shrink down the variability or find some way to increase the magnitude of my effect, it's going to start to impact sort of the power of my tests. Okay, so let's say, Riley, you're doing a study looking at sort of trauma-related stuff, right? And you're looking at differences in, say, social functioning for individuals with PTSD and without PTSD, right? If you just grab people who have had trauma versus those without trauma, that difference is probably going to be pretty minimal, right? It's going to be hard to find it, right? But if you go through and you take people who have never experienced any trauma ever in their entire lives, they've just had charmed lives, versus people who sort of meet severe PTSD, what happened to that effect size that you're looking at?
It's going to go up.
Yeah, it's gotten way bigger, right? And so different strategies that we can use also, let's say, Ari, you're interested in looking at, spatial stuff, right? And so you've got a measure that's sort of really ugly and kind of dirty. It's a self-report measure that's not that good. It's got a lot of error, right? And then you'd run a separate study that where you're using a much more precise measure of spatial reasoning and things like that, right? That much more precise measure relative to the really dirty measure that's got a lot of error, that's going to increase the magnitude of your effect, right? Because you got a lot more precision. You're dealing with less static, right? So as we're thinking about power, thinking about our design, how do we go through and start to adjust things to increase the power of our tests to make it more likely that we're going to find the effects that we want to find or that we're looking for? Because otherwise, we're kind of running out there on a hope and a prayer, right? I've got a cool idea, but the likelihood of me finding an effect that's, even if it is there, starts becoming vanishingly small if I don't have adequately powered tests. Okay. So this is a lot talking about power, but really wanting people to get sort of a sense of this in their head. Questions about sort of different ways of thinking about power, or kind of how this all works out, fits together.
So the
Yeah.
shaded part, the like lightly shaded part, that represents type 2 error.
Yeah, absolutely. Okay. Because, Riley, in both of these situations, right? So this is my assumed distribution under the null, right? But this is real life. H1 is real life, right? So, but in real life, I could get a score that falls anywhere along this distribution, right? But if I find a score that is anywhere on the other side of where this alpha level is, even though it's coming from a distribution that doesn't have a mean of 80, it's still, my score is still falling is something reasonable that I could find in a mean that's in a distribution that's has a mean value of 80, and so I'm going to reject the null, right? But over here, this is my power. These are all the values under H1 that are going to fall beyond my alpha level, right? And so this is all the stuff that where I'm going to reject the null, right? But it's a smaller portion of of the possible values that I could get relative to the body of this, right? And so this would be a situation where I have underpowered test versus down here, right? I've still got a good portion of my distribution that I could find that would be reasonable to find under H1, but are still going to fall to the left of my critical value. But I've got a larger portion of here of values that I could find that are falling beyond alpha, and so this is going to be a much better powered test here. Cool.
So regarding, kind of going off that, so regarding the area and the H1 distribution to the left, is that's type 2 error or type 1 error?
Excuse me. So H to the left.
Just like where you wrote, like right here where it says distribution, under a heavily shaded area in the tail of right here, the red one. What is the B? Is that a beta or what
Yeah.
is that beta?
Yep. This is beta. Beta is your type. Beta is your type 2 error. Alpha is your type 1 error. Beta is your type 2 error. So 1 minus beta, that's your power.
Oh, okay.
People kind of getting a handle of this, kind of starting to see. It's a hard thing to pick up, but if you go through, spend some time sort of thinking about these figures, once it clicks, it's like a friggin' magic eye poster, right? Like once it clicks in, you're like, okay, so there we go. But sort of go through, take a look at this. Power is one of those things that people commonly misunderstand and will make statements about it that aren't true, or sort of make decisions that are probably not informed. Just because a lot of people will look at this and be like, I don't know, that seems confusing, so I just hope I never run into it. But it's an important thing to be thinking about as we're going through and planning and designing studies. All right. So influences on power, things that will impact your power, effect size, okay? The magnitude of the difference in the population is going to impact your power. Here, this is the primary difference we're seeing. Figure 8.2, this is a situation where we have a larger effect size than right here, right? And so this is going to be a more powerful experiment than this is, just because we have a bigger effect. The bigger effect I have, on average, everything else held equal, the more power I'm going to have to detect my effects, and so the more likely it is that I'm going to reject the null hypotheses, okay? My alpha level, if I increase my alpha level, if I say I'm going to set alpha equal to 0.1, well, that's going to increase my power, right? Because it's going to make this area smaller, or excuse me, it's going to make this area larger, and there's going to be more of that falls in there, right? But other consideration, do we get to choose our own alpha level? Not really, right? Because we have convention, right? If I try and publish, Erica, let's say that you're going to publish something in JPSP, and you say, I'm going to set my alpha level to 0.15, right? Are they going to handle that? Nope, they're going to say, nice try, and send it back to you, right? So it starts to become hard. There are situations where we could make arguments for increasing the size of our alpha, but it's going to be hard to, it's a hard sell, right? So that's generally pretty fixed. Population variance, right? As the variability of my distribution increases, as my population variance increases, that's going to increase the variability of my sampling distribution to some extent, right? but we often can't do much about our population variance, right? Population variance is what it is. But as our populations become more variable, it starts to increase the variability and sort of makes it our tests less powerful. But the big thing here is going to be our sample size. Okay. Oh yeah. What do we call the variability of sampling distribution? Brittany?
Erica just said it. It's the standard error.
Yes, standard error, right? So again, as remember our standard error in the simplest one sample test, standard error, the mean is population variance over square root of n, right? So we know that as population variance increases, it's going to increase our variability of my sampling distribution, right? But the big thing that we can go through and start to impact power is the biggest influence is going to be our sample size, right? The variability of my distribution of sample means gets smaller and smaller and smaller as my n gets larger and larger. And so generally what we're doing when we're talking about trying to maximize power is going to think about trying to increase our sample size. Okay. Now there are other things that we can do. We talked about there are strategies that we can use to try and increase our effect size, right? I can use experimental manipulations that are more powerful, right? So Eric, I keep coming back picking on you, but let's say I'm doing an anger study, some of the stuff that Ben's done before, right? I could bring people into the lab and have them think about sort of some angry memory, right? And that's probably going to increase anger or something like that, right? Or what I can do is I can have a confederate that sits there and trolls them and says things to make them angry and actively provoke them, right? That's going to be a stronger manipulation than just having someone think about things. And so that could be a way to go through and increase my effect, right? Clinical folks, right? We'll see a lot of extreme group designs, right? So we're saying, oh, here's people who have some level of depression versus people who have lower levels of depression. That's whatever I'm looking for, probably going to have a smaller effect than if I use an extreme groups designs versus here's people who have never had a psychological difficulty in their entire life against someone who has been repeatedly hospitalized for depression, right? We're just setting up a design that maximizes that effect size, right? Measurement also comes into play. If I've got better measurements, it cuts down the static and makes that effect bigger. But in general, what we're typically doing is we're looking at increasing our sample size to go through and increase power. Oh, there's a sort of a low-hanging fruit part. Brittany likes it, right? I gauge my success in groans from all of you. All right. So let's do this. Let's take a break here. Okay. Go through. Take 10. Let's try and be back at 3:15. Let's say. And we'll come back in. We'll start talking about estimating power and going through and or estimating effect sizes and how we go through and start to set up some of these power analyses. Okay. All right. All right. Okay. Questions about power or the conceptualization of power or anything we've covered up to this point in terms of thinking about sort of this idea of type 2 errors and sort of the extent to which our studies are powered. Kind of getting the handle on this stuff. Cool. All right. We'll jump into... Oh, there we go. Okay. So if we're going to go through and calculate power, what we need to do first is we need to estimate or get some measure of the effect size that we're looking for in our studies. Okay. Right now, all of you to differing degrees, maybe starting to think about thesis projects, right? And eventually you're going to get a research question. You're going to say, okay, this is what I'm going to go through and look for. This is my question. This is the association or effect that I'm wanting to detect or test in my study, okay? If you're going to run a power analysis on this, what you need is to be able to, for some way to go through and find sort of get an estimate of about what size of effect we're going to go through or you're going to go through and try and target. And the best place for this is going to be existing research, okay? hopefully there's some other study out there that's done something that's kind of similar to what are looking to do, or has used similar methods or things like that, where you can go through and you can say, okay, Poole et al. 2020 did something similar to what I'm looking for, and this is what they found. Okay, and so it looks like they found looking at differences of Group A and Group B, found an effect of about 0.43. D equal 0.43, and so that's what I'm going to use as my effect. Okay. Now the risk there is that Poole et al. Is a one-off study. Who knows if Poole et al. Did their estimate of effect is sort of a good one, or if it's overinflated. This is where our meta-analyses come into play, right? This is going to be an aggregate, and so probably going to be a much more stable effect. But going through and looking at existing research is going to be our best way to go through and take a look. And again, trying to say, okay, look at the range of effects that have been found to come up with some reasonable level. This is also important why reporting, this is also a reason why reporting mean standard deviations, relevant statistics is important in our studies, so that other people can go back through and, let's say Robert's running a study and he collected some measures, but wasn't really part of what he was interested in, but Eric is interested in sort of these things. And so if Robert's reported correlations mean standard deviations for everything, Eric can go through and use that data to go through and detect an effect size, or sort of calculate an effect size, even if Robert's never sort of reported it, right? So just being thorough in our reporting starts to become important. So existing research, but sometimes we're looking at stuff and there's no one that's done it before, okay? Again, let's say Riley or Natalie, you and Riley are looking at assault prevention types of programs or something along those lines, right? And no one's ever actually tested sort of this sort of program before, right? And so there's no existing research to look for an effect size because it's brand new. What you might do here is start to take a look and say, how large of an effect would I need in order for this to be a viable program, right? And so you might say, based on literature, you say, well, existing sort of stuff that's already out there is seeing an effect size of, say, 0.6. So what we would need to do if our studies, or if our project or program is any good, we'd need to see an effect size of at least 0.6 to make it viable. Otherwise, there's other stuff that we can use. And so what I could do is, even though there's no effect size for me to find, because I'm the first person to do it, I could say, this is my target. And if it's not at least at that level, then things start to be questionable on whether or not this is going to be viable or not, right? So here, an example, we could say, I'm interested in some skills training to increase the GRE, right? And I'm just going to say that I need to, if my program doesn't increase GRE scores by 40 points, then it's not going to be worth the time and effort and things like that. So what I can do is I can go through and I can say, okay, here's my effect size that I would need to find. I'm going to power to my study to that level. And so if I don't find anything, it means either that there's not an effect there that's sort of worth getting, or if it was at this size, I should have been able to detect it and sort of working from there. Okay, so it's a little bit different. Here, you're using existing research to try and get a gauge for what type of the magnitude of effect you're likely to be searching for. Here, you're kind of calling your shot. Other thing that you can do, and again, this is something that you should be doing when you're kind of out of other options. What you can do is you can start to use some conventional cut points for certain magnitude of effect, large, small, medium, and large. Okay, so if you are, and if I'm doing more experimental work or sort of theory-based research, right? There may not be anybody who's actually looked at this mechanism. I don't know that I need to, there's some sort of minimum effect size that I would need to find in order to make this viable, because I'm testing a theory-based mechanism. And so maybe what you do is you say, I'm going to power my study to detect a large effect, a small effect, a medium, or a large effect. Okay. But you should really be doing this when you have no other options. So there should be like literally no other studies that have looked at anything even close to what you're doing. Or there's really no way to say this is the minimum effect I would need in order to make this study viable. Then maybe we can start falling off on benchmarks. But the thing is, And we need to be realistic if we're doing this, right? See this all the time. I reviewed a paper last week that said, okay, we're powering our study to detect a large effect, okay? With no basis, seemingly, for any reason to expect that you're looking for a large effect. Anybody guess sort of what the magnitude of effects we're typically searching for or working with in psychological science?
Is it small?
Yeah, it's small, right? We've got nasty, dirty measures that are full of static. The differences that we're looking at are generally pretty subtle, right? If we're going to do this, unless you need to have a good reason to make an argument for why you're looking for a medium or large effect, but if you have a good reason for that, you probably have something in the existing research, you should just already do this, okay? So just wanting to make sure the whole idea is to provide some realistic assessment of, given what I'm wanting to do and the resources I have and the people that I can collect, what's sort of the long-term probability of me identifying this effect if it is in fact there, okay? Right? Howell, in his text, talks about, when he's talking about estimating effect sizes, says, I don't know, often translates into, I haven't thought that far ahead. I would make an argument like, oh, I can't, means that you didn't try or didn't look hard enough, right? There's probably something out there that you could at least say, okay, sowers that all went through and looked at this, they're doing a different thing with a slightly different population, but at least it gives me a ballpark. I'm probably going to find something about there. So going through, knowing your literature, doing your homework is going to be very important here. Okay. Questions on this? All right. So when we're calculating power, something that comes up that we need to be aware of and be thinking about is something we refer to as a non-centrality parameter, okay? Now, my t statistic, and let's say we're using a single sample t here, okay? I'm testing some estimate of a population parameter, population mean against some reference value, right? This t statistic, the distribution of this t statistic is going to be centered around 0 so long as my expected value under the null is accurate, okay? So if I'm calculating a test statistic and say my null value is 50, as long as the population from which I'm pulling from actually has a null value of 50, or actually has a population value of 50, that t statistic is going to be distributed around 0, right? Some t values in some replications are going to be positive, some are going to be negative, but they're going to be distributed around 0, okay? But if that null value is false, right, and our mean for our population that we're interested in isn't equal to the value under the null, what we find is that t distribution is no longer centered around 0 because we're subtracting the wrong population mean, right? If I'm saying my value under the null is 50 and I'm subtracting 50, then my t distribution is going to be centered around 0, right? But if my value under the null is 50 and my actual population mean is 60, then I get a shift, okay? My t isn't going to be distributed around 0 anymore because I'm subtracting the wrong thing, right? In this situation, my t is going to be distributed around some other value, okay? And where we'd say in this situation that our t distribution is a non-central t distribution and it's centered around the point delta, okay? Delta is the new center point or the new midpoint for this t distribution. And this shift from 0, the value expected under the null, to delta, this is going to be my degree. We refer to this as our degree of non-centrality, okay? And delta here is going to be our non-centrality parameter, right? So if, again, the null is true, and I'm subtracting the true population null value from, on average, the values I'm getting from my mean for my sample, then everything centers around a nice central t distribution that we have in tables and things like that. But we're hoping that doesn't happen, right? We're hoping to find evidence against the null. We're hoping that my t-distribution isn't centered around 0. It's centered around something else. That something else is going to be delta. This is my non-centrality parameter. And if we're thinking about power, we can think about how likely we are to find the value of a non-central distribution, which is here, that's greater than the critical value under my central t distribution here. Okay, so this is why that overlapping distributions conceptualization starts to help when we're thinking about sort of how we go through and find this non-centrality parameter. Okay, and this non-centrality parameter, this delta, this is sort of a reflection of my effect size. Okay, as my population mean starts to get increasingly larger or increasingly different from the assumed value under the null, my distribution starts to shift out here, right? Meaning the effect size is getting larger and larger. Okay, people see what's kind of going on with these distributions. All right. So when we're going through and we're calculating power, what we need is some estimate of this non-centrality parameter, right? And again, the non-centrality parameter is kind of a metric of your effect size. As your non-centrality parameter gets larger and larger and larger, it means your target distribution is less and less overlapped with your null distribution, meaning that you've got a larger and larger effect size. Okay. So if we're going through and calculating power, what we're going to do is we need to use that effect size to go through and calculate some use that effect size to calculate a non-centrality parameter that we can use to then calculate power. Okay, so what we're going to do, if we're taking the single sample test, what we're going to do is we're going to start to use some tabled values to start to calculate our non-centrality parameter and alpha to go through and sort of make some estimates if we're going to hand calculate power. And so this is where, all right, pull up your non-centrality parameter or your power table that I posted here. What we see is this is what we've tabled. Power is a function of our non-centrality parameter and our level and our delta level here, or excuse me, and our significance level, our alpha, right? Here, we're almost always going to use 0.05 because that's just the alpha level that we generally use. But what we can do is we can start to, this table has values of power that correspond to different non-centrality parameters and different alpha levels. Okay, so if we go through and we take a look, okay, we have for our single sample test, D, our effect size is going to be our some mean value minus whatever the reference value is over a standard deviation estimate. Our non-centrality parameter is going to be equal to our effect size times the square root of the sample size. Okay. So let's take an example. So there's sort of pop psychology says, people with higher IQs, people who are higher IQs are too smart for their own good, right? The geniuses are always crazy. People with psychological problems may have higher IQs. Is that sort of, I don't think this is true, but it's sort of the example that we're using here, okay? And so what we're interested in is saying, do people who are seeking treatment for psychological problems have higher IQs, right? So we go through and we sample 25 individuals from, let's say, an outpatient clinic who are coming in for some sort of thing, and we find that they have an average IQ score of 105, right? Well, we know that the mean for IQ is 100, standard deviation 15, okay? And so what we can do is we can take 105 minus 100 divided by 15 to get our estimate of our effect size, okay? This gives us a D of 0.33, okay? And you can do this, right? If I take 5 divided by 15, give me an effect size of 3, right? So I'm saying, based on my effect size, I would say data that I've collected from data I have available to me, suggesting about that individuals seeking outpatient treatment for psychological difficulties are scoring about a third of a standard deviation higher than sort of the general population on IQ, right? That's just my D, right? But what I need to do is I need to transform that D into a non-centrality parameter. So what I do is I take 0.33, multiply it by the square root of 25, and if I do that, let's see, I get 5 divided by 15, 0.333 times square root of 25 is 5. So I've got a delta of, let's say, 1.67. Okay. So what I would do then is I could go to my non-centrality or my power table, and I go through and I find delta 1.67. Is that right? Yeah. It's going to fall somewhere between here. If I look at my table here at 0.05, that's going to say that my sample of 25 for a single sample t-test, assuming an effect size of 0.33, I'm going to have, in sort of this future study that I'm going to replicate this, I'm going to have power somewhere between 0.36 and 0.4. People see where I got this? Okay. So, let me get out of here. All right. So what I would do is I would say, so I would just split the difference here and said power is about 0.38. So we would say, assuming the null hypothesis is false, effect is expected to reach statistical significance about 38% of the time given a sample of 25 and a population effect of 0.33. Okay. Robert, am I happy with this level of power?
No.
Yeah, why not?
I mean, it's pretty low if you're going off of that 0.80 standard.
Mm-hmm. It's saying less than 40% of the time am I going to find this effect. This effect is out there. Assuming the null hypothesis is false, if I'm looking for an effect size with a single sample t-test, and my effect size is 0.33, and I'm only using a sample of 25, I'm gonna miss more than 60%. More than 60% of the time I'm gonna make a type 2 error. Okay, we shouldn't be excited about that, right? Because that's saying that even though there is an effect out there in the world, we'll say 62% of the time, I'm going to be able, based on this test, I'm going to be able to say, I don't know if there is an effect or not, right? So we've got an underpowered test. So what might we want to do here, Ari, in this situation? So I know that 25 isn't enough to adequately power a single sample t-test looking to find a test, an effect size of 0.33. So what might I want to do? Yeah, I might want to know how big of my sample. So, okay, so 25 isn't enough. What do I need, right? And so the question is, what's the sample needed to achieve power of 0.80? Okay, well, what we can do is we can just do a little bit of algebra, right? So here, we've got delta is equal to d times the square root of n. I just use some algebraic magic and sort of flip this around. I get the sample size that I need is going to be equal to delta, delta over d squared. Okay, and so if I do that, I go through and I get n equals 2.8 over 0.33, and we square that up. Where did I get 2.80?
That's the delta needed to have a power of 0.8.
Exactly. Nice work, Allie. If I go through and I look at my table, right, and I'm looking at 0.05, right, and I go through and I find, okay, what delta is associated with power equals 0.80? It's 2.8. Okay. So what I do is I say, okay, if I'm looking for a non-centrality parameter of 2.8, because that's what's associated with power of 0.80, if I take 2.8 divided by 0.33, square that. So someone tell me, run these calculations. How many people, if I'm using a single sample t-test, and the effect that population effect I'm looking for is 0.33, how many people do I need to have in this study to have an adequately powered test?
72.
72. Okay. So again, what we can start to do is we can say, okay, one, if I'm thinking that I'm chasing an effect size of 0.33 and I can only get 25 people in my sample, with a single sample t, what's the power of that test? What should I expect the power of that test to be? Answer is not good, right? But what I can also do is I can say, okay, this is the effect size I think I'm chasing. How many people do I need to have in order with a single sample t-test in order to make this adequately powered? Flip this around, go through and do it. It's telling me I need about 72 people. Okay. People see how we went through and you use this to go through and run some simple power calculations? All right. Okay, so that was our single sample test. What if we want to do an independent sample t-test? Okay. Now remember, an informal assumption of our independent sample t-test is that we have equal sample sizes. So things start to get pretty easy and straightforward if we're going to calculate power for an independent sample t-test where we've got the same number of people in group 1 and group 2. Okay. And so if I'm looking for the power to detect a difference in sample means, again, my effect size is going to be the difference in mean 1 and mean 2 over some standard deviation estimate, right? My non-centrality parameter here is going to be a little bit different. It's going to be d times the square root of n over 2, where n is the number of cases in either sample, because in this scenario we're using equal samples, right? So n doesn't matter. If I got 20 people in this sample, 20 people, it's just 20 over 2. Okay. So let's say I'm interested in looking at the difference in symptoms in symptom means for treatment 1 versus treatment 2. Okay. So I know that the difference in the means that I found is 0.5, or this is some previous research, right? Some other study has gone through and done this, and they found a difference in symptom symptom means for treatment 1 and treatment 2 is equal to 0.5. We've got we'll call it an average standard deviation of 10 across this, and this is all pulled from existing data. And I'm saying I've got enough people to calculate or to grab 25 people from each group, right? Okay, so my effect size is going to be the difference, 5 over 10, right? Because that's my standard deviation. It's going to give me an effect size of 0.5. Take 0.5 times the square root of 25 over 2, okay? Right? Because this is just 25 in each sample, right? So 25 over 2. Someone tell me what my non-centrality parameter is here. Someone with a calculator.
1.77.
What is it, Allie?
1.77.
1.77, okay? So if I go through to 1.77 in for my non-centrality parameter, somewhere between 1.7 and 1.8. So it's looking like I have power that's somewhere between 0.4 and 0.44 for this test. Okay. And so again, we would say power is about, we'll split the difference, call it about 0.43. Say assuming the null is false, the effect is expected to reach statistical significance 43% of the time given n equals 25 per group and a population effect of 0.5. Okay. So again, Rachel, am I excited about this, the power of this test?
No, not really.
No, I'm not, right? It's saying over half of the time I'm not going to find this effect, even though an effect is there. And honestly, not a bad effect size, right? 0.5, if you think about our benchmarks, this is consistent with benchmarks for a medium effect, right? So even with a medium effect, something that's there and from Cohen's standard is something that we should be able to sort of notice just by looking at it. Over half of the time, we're still not going to be able to identify sort of this effect, even though it exists, right? And so what we can do if we want to know the sample per cell needed to achieve adequate power, Again, we're just taking our delta formula, rearranging it, right? And so the sample we needed to achieve a power of some set size is going to be now equal to 2 times delta over d squared, right? So here it's going to be 2 times 2.8 over my effect size is 0.5. I'm going to square that up, okay? Someone run these numbers for me. Tell me how many people for this study, if I'm using an independent sample t-test and I have equal samples and I want to go through and detect a medium effect, how many people do I need in each group?
$63.
63? Is that right? Other people get 63? Okay. So that's a lot, right? I mean, that's a decent, for a means-based test, 63 is a lot for an individual group, right? But even if we're looking for something that's a medium effect, and this is probably an effect that's bigger than what we can generally hope for with these types of with the types of things we're usually doing, that's a lot of people to adequately power. Okay. Questions about what we did here, how we're finding this? All right. So this is if we have equal samples, okay? So we've got equal number of people, but oftentimes we don't, right? Now, Erica, Brittany, Ari, for a lot of experimental designs, if we're sort of going through and assessing and sort of putting people into randomizing people to condition, right? A lot of times we can say, okay, we're going to sort of randomize people relatively equally and sort of have equal sample sizes, right? But sometimes you might be working with situations, clinical folks who are often doing this if we want to look at people who are symptomatic versus not symptomatic, or experimental folks if you're looking at pre-existing factors, sort of background characteristics. You might not say, I don't know that I can get, sort of in our type of stuff, men are underrepresented in our studies just because it's harder to get bozos in and sort of participate in research and stuff like that, right? So we might not be able to get equal samples. So maybe we don't. Maybe we're going to have unequal samples, right? Or maybe I know that I have enough resources to collect this many people from this group, but only this many from this group. What we need to do is we need to start making adjustments here. And what we need to do is calculate a harmonic mean sample size to adjust for this unequal samples. And so your n, your harmonic n, is going to be equal to 2 times the number of people in your first group times the number of people in your second group over the number of people in your first group plus the number of people in your second group. Okay. So if we go through and we go back and we think about the stereotype threat example we did at the beginning of the lecture, okay, let's say that for some reason, I know that I'm going to have more control people than my threat group. Okay, and so if we have mean of 9.64 for my control, mean 6.58 for my threat, and I'm pulling this from previous research, right? And I know that I'm going to have an imbalanced number of people that I can collect. Let's say I'm going to target 18 for my first group, 12 for my second group, and based on the original study, I have a pooled standard deviation of 3.1. Okay. What I would need to do is I would need to go through and calculate my effect size, right? Sort of based on previous research. This is going to be control minus my threat over my pooled standard deviation, right? So that's going to give me an effect size. My effect size is 0.99, okay? But what I need to do now here, instead of to get my delta is d times n over 2. Well, here I have unequal samples, so I need to plug in my harmonic n, right? And so I need to calculate my harmonic n as 2 times 18 in my first group times 12 in my second over 18 plus 12 is going to give me 14.4. Okay, so I plug in my harmonic n, 14.4 divided by 2. Someone tell me what I get for power here, or for my non-centrality parameter.
is it like 2.65, and that equates to the power of 0.75?
You
Yeah.
got a nonce of 2 point. What did you get, Brittany?
2.65.
2.65. Okay.
Yeah.
So 2.65 is going to put me between 0.74, 0.77, right? About 0.75 here. Okay. So I would say, assuming the null is false, expected effect or effect is expected to reach statistical significance 75% of the time, given samples of 18 and 12, with a population of effect of 0.99. Okay. Brittany, are we happier with this?
Yes, because it's really close to large.
Yeah, right. I mean, we're identified. We've got a massive. This is saying that sort of based on this 98 study, it's saying the effective stereotype threat is massive. Now, I'm not a social psychologist, but talking with Sean and Ben about this thing, I don't know that stereotype threat is that big of an effect. And so if that's what I found, I might want to think about maybe thinking if that's a reasonable estimate of effect. But if it is, and I'm looking for a really, really large effect, I'm still a little bit underpowered, but I'm closer, right? Now the thing to notice here is that if my harmonic n is 14.4, right? And if I take 14.4 and multiply it by 2, so I've got sort of 2 samples here, I get an effective sample size of 28.8, right? Which is less than sort of the actual number of people in my sample, which is 30, okay? So what does this imply for the impact of unequal samples on the power of your tests? What do you think, Riley?
Is it underestimating it?
Yeah, it decreases my power, right? So again, if I have relatively equal samples, and this isn't too much, this is a difference of 6 people, right? But effectively, when I'm calculating my power, it means that I'm working with a sample of just under 29 versus the full 30, right? But if I'm doing stuff, and this happens a lot in clinical research, right, where I've got maybe 15 people who have some condition and, 40 people who are in my control group. So I have a sample of 55, but actually I'm not sort of getting the same powers as if I would have a sample of 55 because I've got this huge imbalance, right? So we're getting penalized in a lot of ways for the extent to which my sample is imbalanced. So wanting to think about that as a concern. Okay. All right. So last thing is our paired sample test. Okay. With our paired sample test, the thing that we need to know with our paired samples is we need to account for the correlation between measurements on our paired sample test. Okay, we need to know how much, if I've got the same group of people and I'm measuring them once and measuring them twice, how strongly are those 2 measures correlated with one another? Because that starts to have a big impact on our power. So to calculate the effect size, an effect size that we would use for the calculation of power for a paired sample test, it's going to look a little bit different, right? For the calculation of power, we're going to take the mean of the different scores, right? Mean at time 1 minus time 2 over a standard deviation of x1, x2, right? And the way we calculate this is we're going to take a standard deviation estimate and we're going to multiply it times 2 times the square root of 2 times 1 minus the correlation of time 1 and time 2. So again, remember sort of back when we were talking about a paired sample test, we talked about had this measure of effect that had our D or Hedges G estimate, right? The mean of the difference scores over a pooled standard deviation estimate, right? Take that divided by 2 times 1 or the square root of 2 minus, or 2 times 1 minus the correlation between type 1 and type 2. That's where this is coming from. This estimate of effect is related to the effects that we're going through and calculating power with. So let's take that stereotype threat study and reconceptualize this as a paired sample test. Okay, so instead of having one group of 18 folks who are going to be my controls and another group of 12 that's going to be my stereotype threat group. Let's say instead I transition this over to a repeated measures design. And let's say I bring these folks in and I go through and I just have them complete this exam. Okay. And then what I do is I say, okay, done that. Here's a second task. What I want you to do, same math task, but this time just like, PS, Asian American students tend to do better on this. And then give that to them. Okay. So instead of having a between samples design, I've switched this over and now I've got a repeated measures design. People see what I'm sort of how I switch this around? Okay. So with the repeated measures design, we'll say performance at time 1 is 9.64. That's same what it was, right? But let's say at time 2, it's now sort of average performance under stereotype threat is 7.55. Okay, so it's a less of a difference, right? But let's say I've got 30 people in the sample, right? Same sample as I had before, except it's just 30 this time instead of having 2 different groups. My pooled standard deviation at time 1 and time 2 is 3.1. My test retest is 0.92. Okay, so the correlation of my scores within subjects at time 1 and time 2 is very high, very strongly correlated, which makes some sense, right? So if I do this, I'm going to go through and calculate my estimate of the standard deviation of the difference, right? I've got 3.10, which is my standard deviation, times the square root of 2 times 1 minus 0.92. Okay, this gives me 1.24. I take time 1 minus time 2 over 1.24. Someone tell me what I get here. $1.685, right? So 1.6, we'll call it 1.69.
It's right there.
No, that's it. Thank you for going through and calculating. No, I just want you to go through and see where. No. Don't laugh at yourself. You're doing awesome. All right. So we got our effect size here times the square root of our sample size, which is 30. Someone new, tell me what I get in terms of my delta parameter here.
About 42.
What's that, Natalie?
About 42.
About 42. Okay. Is 42 on this table? No, right? So basically what this is saying is it's if my actual effect is about 1.69 with a sample of 30 and a paired sample test, what this is telling me, I've got near perfect, functionally I've achieved perfect power. Like I will 100% of the time identify this effect. Okay. So what's going on with the power in this example? Okay. Because what I've done is I've got the same number of people as our between subjects example, or as the between subjects scenario. I got the same number of people, right? And the absolute difference in scores across my control condition and my threat condition is actually quite a bit less. But last time with the between sample test, I had power of 0.75, which was pretty good. But in my repeated measures example, my power is functionally perfect. I'm 100% guaranteed, almost a certainty that I'm going to detect an effect. What's going on between these two scenarios? What do you think, Allie?
I mean, I don't know about like the calculation, but like in terms of the methodology, like you've kept the people the same, and so you're reducing some of that like potential error.
Yeah. And so even though we're finding less of a difference in people sort of first taking a control and then giving them the stereotype threat, even though the difference there is smaller than what we saw in the previous study, we're still way, way, way more powered with this. This just speaks to the power of our repeated measures designs, okay? Far greater power with smaller differences than we get with our between subjects designs. Again, because we're starting to reduce variability due to just random individual differences. Okay, and what we're also doing is we're capitalizing on the correlation between assessments, and this starts to make for very, very, very powerful tests. Okay. What we start to do with these repeated measures designs, we parcel out systematic between subject variability. Okay, so all of the things, if I were to give you all a self-report measure of mood right now, okay, some of your scores is going to reflect kind of your general mood, right? But there's a lot of other stuff that's going to go through and reflect individual differences, the effort that you put into it, just how you respond to scores. All the stuff that makes you all different and unique people gets dumped in this error term, right? And so if I've got one group of folks and another group of folks, and I'm comparing the two, there's a whole lot of noise there just due to individual difference characteristics, right? But if I have one group of people and I measure them on two separate occasions, what ends up happening is everything that makes Rachel unique from the rest of you at time 1 is controlled when we measure Rachel again at time 2, and so all of that difference gets sort of parceled out. Because all we're looking at is the extent to which Rachel's scores are going up or down relative to the first time. Same thing with everybody else, right? And so what we end up with is a reduction in overall noise, and it makes for a much, much, much more powerful test when we're going through and doing this. And we see that this correction between our repeated measures designs and our between subjects designs in terms of an increase in power ends up being a function of the correlation between our two measures, okay? So if I've got a repeated measure, if I'm measuring something that's very, very stable across repeated assessments, so I think about, has anybody done previous work with like psychophys types of stuff? Anybody ever done any psychophysiology research? Okay. Well, if you've done it, if you look at something like skin conductance, right? We're looking at a biological rhythm, and if I measure Robert's skin conductance right now and 5 minutes later from now, it's kind of constrained to the extent like Robert can't sort of start in one area and then his physiology changes in 5 minutes and he's starting in a completely different area, right? And it's a biological system, right? Like it can't just be whatever it wants to be. If I'm asking Robert how he feels right now and how he feels 5 minutes from now, who knows where that's going to go? Robert's not a stable person. He sort of routinely is all over the place in how he feels about things, right? Not really. But with a biological system like this, what we find is very, very, very strong correlations between what's going on at time 1 and time 2, okay? And when this happens, we have very, very strong correlations between those two, which makes for a very powerful test, okay? But the advantage of our repeated measures design starts to decrease as this correlation starts to approach 0. Okay, so if I'm getting a lot of variability, if Robert's score at time 1 starts to become non-predictive of his score at time 2, basically what we're doing is we're reducing, even though we're using a repeated measures design, that it essentially functions to reduces down to an independent sample test as that correlation starts to push down closer to 0. Okay, so take-home message here is that if it's at all possible to incorporate a repeated measures design into any type of analysis or any type of study you're doing, you absolutely should do that. It's going to be huge in terms of identifying effects. It's going to be huge in reducing the number of people you need to have to adequately power a test, right? Even if I'm looking for something very, very small in terms of a theoretical effect, if I can use a repeated measures design, it's going to make it much more likely for me to be able to detect that. Now, there's going to be some situations where I can't, right? There's going to be situations where testing effects, carryover effects are just going to make it non-feasible to be able to go through and run a repeated measures design. But if we can, if there's a way to finagle it, strongly recommend to be thinking about repeated measures assessments and repeated measure tests, because it just makes your design much, much, much more strong. Okay. All right, questions on any of this? All right. Going to do some quick calculations. So what we've been doing up to this point is going through doing hand calculations with power, right? We're going through doing some basic hand stuff using our power table, but this is pretty limited in a lot of different ways, just because it's hard to. There's just better ways to do it now. So we're not having to crank out hand calculations. A lot of different things go on. Things are pretty simple for these basic means-based tests, but as we start to get into other areas, it starts to get more and more difficult, right? And so what we've got is some pretty slick and easy ways or tools to go through and start to calculate power, so that we don't have to do it all by hand all the time. Okay. So here is G-Power. Has anybody used G-Power before? Sort of familiar with G-Power? Know that it's a thing? Okay. It's a free online tool. If you go through, if you Google or Firefox or whatever you use to sort of get your stuff, G-Power, it'll come up. You download it. It'll be a little desktop app that you can place up there. Pretty easy peasy. Okay. And here what we can do is start to streamline our power calculations in a way that sort of is kind of nice. Okay, so let's say that I've got looking at a single sample t-test, right? And what I'm interested in is looking at CAP scores in first responders relative to some normative motor vehicle accident. So CAPS, for those of you who aren't in the trauma world, this is a sort of interview measure of PTSD. And what I want to see is whether or not first responders systematically score higher than, say, car accident survivors on this measure of interview measure of PTSD. Okay, so I'm going to say that I've gone through and I'm expecting, based on previous research, for mean levels of CAP scores for first responders to be 65.3 with a standard deviation of 13.5. And my reference value that I've determined from whatever is for motor vehicle accident survivors a score of 70. Okay, and I plan to look at this with a single sample t-test. But what I want to know is how many people do I need in order to adequately power this test. Okay, so what I can do is I can go over to G-Power here. I'm going to go choose t-tests, and I'm going to look at mean difference from constant. Okay, this is my single sample T. I'm going to select this. Okay, I'm going to pull this over here because it just makes more sense to me. All right, so I've got my t-test, difference from a constant, one sample, and I want to compute the required sample size given alpha, power, and effect size. Okay. So I need to determine what my effect size is. Now I can just go through and calculate my effect size by hand, but what I can do is G-Power. Oh, whoops, we can't see that. There we go. If I hit determine, what I can do is I can, well, it's wanting me to plug in stuff that I don't want to actually plug in here for the single sample test. Okay, never mind. I'm going to calculate this by hand. So someone do this for me. Someone take 65.3 or 70 minus 70.1 minus 65.3 and divide it by 13.5. Tell me what I get for my effect size here. Oh, I'm sorry. Never mind. Scratch that. I was looking at the wrong stuff. Okay. Here, I'm going to hit determine. Mean under my null is 70.1. Mean under my alternative, 65.3. My standard deviation, 13.5. And calculate my effect size. Looks like I got effect size of 0.36. I'm going to hit calculate and transfer to main window. Plugs it over there. we're good to go. Okay. Now, alpha level 0.05, and what do I want to set as my power? What do you think, Ari?
Sorry, that's our power. That's good. Sorry.
Oh yeah. So yeah. So what do I want my power to be? What do we? What's our benchmark for establishing adequate power?
0.80.
Yep. Okay. So G power is going to give me sort of more power than I sort of necessarily need. So I'm going to switch that over to 0.8. Going to calculate. All right. So here is calculating my non-centrality parameter for me. My critical T. Oh, whoops. Two-tailed test. There we go. Calculate. There we go. That looks better. Okay. Here's my non-centrality parameter. My critical T for a single sample test at alpha 0.05. Degrees of freedom. So here's my total sample. So I need, what G power is telling me is I need 65 people in order to adequately power this single sample t-test to get an effect size, to identify an effect size of 0.35 or 0.36. Okay. So just a quick, simple tool to be able to go through and do this. Easy peasy, right? Questions about how we use G power here to plug stuff in? All right. Let's do a different one. Let's say we've got an independent sample t-test, okay? And I'm looking at, this is just pulling back from an example that we used when we were running through t-test stuff. We're looking at gender differences in marital satisfaction following disaster among Hispanic immigrants, let's say, okay? And so we've got data from an existing study that has stuff for men, sample for men and women, and we want to go through and do a replication, right? And we want to see, okay, can we identify sort of the effect in this very specific population, right? So what we're going to do is we're going to go to test statistic, choose our t-test, but this time we're going to go to difference between two independent means, two groups. Okay? We're still going to, for our type of power analyses, we're still going to do a priori. We want to compute the sample size that we would need. If this is representative of the true effect in the population, how many people would we need in our groups in order to identify or adequately power this test? So I'm going to go for a two-tailed test, again for my effect size, and let G power do this for me. Okay. Now I'm going to go through and I'm going to say mean of group 1, 80.2, mean of group 2, 108.9, standard deviation of group 1, 30.4, group 2, 24.4. Calculate my effect size. Cool. Looks like I'm getting a pretty large effect size here. Calculate, transfer over. Okay. Puts my effect size in here. Alpha level is 0.05. I'm going to change my my power to 0.8. And then we've got our allocation ratio. The number of difference between sample 1 and sample 2. I'm going to leave this at 1, assuming that I'm going to get roughly equal samples of men and women here. Okay. I'm going to go through and I'm going to hit calculate. And so for an effect size, if I'm looking for effect size that's about 1, right, looks like I only need about 16 people in each group in order to adequately power this test. So for an independent sample t-test, if the effect I'm chasing is 1.04, about 16 people per group will give me an adequate sample to power this test. Okay. But let's say I'm expecting maybe I get twice as many women as men. Okay. And let's say I'm going to switch this. So I'm going to have unequal sample sizes. So if I keep everything the same, but change my allocation ratio 2 to 1, calculate this, okay, we'll see that this changes, right? So I'm looking at 12 in one group, 24 in the other group in order to achieve adequate power here. Questions on calculation of this?
Not a question on calculation, but just kind of like a psychology question.
Yeah.
That feels like a low sample size to me.
Yeah, it is a low sample
It
size.
doesn't feel like it would be hard to get, but that's a large effect, right?
Yeah.
So is it just sometimes it's like that?
Okay. Yeah. So why do I? You're exactly right, Brittany. We don't need that many people. Why don't we need that many people?
Maybe because of the type of t-test, it's independent sample.
Mm-hmm.
I don't really know.
So someone help her out. Why do we only need, say, 12 and 24 people in order to adequately power this test in this scenario? What do you think, Robert?
I don't entirely know. I'm just gonna take a guess. And, maybe because we're using harmonious mean? No.
Okay, not quite. What's going on here? Allie, what's happening?
Is it because of the large effects?
Yeah. I've got an effect you can drive a truck through. It's huge, right? It would be obvious if you have eyes in your head, an effect of this size, right? If I go down through and I change that effect size into something that's more reasonable, let's say 0.3, because that's often what we're working with in psychological sciences, these small samples. Now look at the sample I need, right? Now all of a sudden we got a very, very different situation going on, right? So this example is just a straight up function of the magnitude of effect that we're looking at here. Okay. All right. So let's go through one more example here, and then I'll turn you all loose for a quick break. Let's say we want a paired sample test. Okay. So again, I'm going to go back to t-test. And so I'm going to go down, and I'm going to choose difference between two dependent means. Okay. This is going to be a paired sample t-test or a matched paired t. I'm going to go through. I want two-tailed tests. Determine my effect size. Okay. What I've got here is I've got my mean at baseline is 4.3. Mean at retest 2.6. Standard deviation at time 1 3.6. Standard deviation at follow-up 3.7. Correlation between groups 0.78. Calculate my effect. Okay. So I've got a decent size effect. It's sort of not quite hitting conventional benchmarks for a large effect, but D equal 0.7 is respectable, right, in terms of effect I'm looking for. So here, my alpha level 0.05, change this to determine my power is 0.80, go through and calculate it. And once again, I am looking at 18 people to adequately power this test. Again, because I'm looking at a medium effect, or sort of a medium-ish effect here, but I'm using a paired sample test with a decent correlation between my two means, or between my two assessment points, means that I don't have to have too much going on here, okay? Now if I go through and if I look at, take the same estimate of effect, difference between two independent means, and I change this to the same effect, 0.701, equal sample sizes. I got much larger. I need a sample size of, instead of like 17, I need 66 people to go through and detect the same effect size with a independent sample test, right? So again, just speaking to the power of this paired sample test. Okay. Also, if I go through and let's say instead of 0.78, my correlation between my assessment points is 0.3, right? So much lower assessment. Now all of a sudden my effect size went from 0.7 to about 0.4. Okay. And now if I go through and calculate that, now I need 53. Okay. But if I go back here and I say my measures are correlated 0.9, now my effect size is way up. And now I need 10 people. Okay. So just showing when we're thinking about the power of our paired sample tests, super, super powerful, but also dependent to some extent on the correlation between our repeated measures. Okay. All right. Questions about G-power or any of these examples that we went through here? Okay. Power write-up, right? You guys know who this is? Okay, Robert, there's got a couple people. No one last time knew what who He-Man was, and we're unaware that he had the power, and it just looked like I had a weird dude in some furry underwear on there, sort of confused people last semester. You guys just much cooler cohort than last semester. But anyway, effect size of 0.5. I'm talking to you, CJ. Effect size of 0.45, expected based on data from Jones and colleagues. Power analyses indicated sample 32 individuals per group would be required to achieve adequate power. Okay. All right. Cool. Let's go through, take a quick break. Let's come back at let's do it short. Let's come back 4:25, and we'll go through and finish up this stuff so we can just be done with power and effect sizes and stuff like that. Okay. All right. What's going on? What?
We were all kind of waiting, and then we started doing nose goes.
And I lost, and I was supposed to scare you.
Oh, okay. See, I thought you'd all be just hanging out in the dark with cameras off, like sort of waiting for me to come back on. I didn't realize I was apologizing to Riley for not being able to keep things in my head for 2 seconds, and so this took precedent. Or turn back
I am
in.
more important. We can just throw that out there.
What's that?
I am more important. We can just throw that out there.
In this situation, yes, and everybody else got a couple extra minutes, right? Like I'm aware that I'm the only. Should we scare? I like that came on like, yeah, I'm easily tricked, I'm afraid. All right, cool. Okay. Any questions before we jump back into sort of the rest of this stuff here? Okay, cool. So power write-up. So one last thing, right? In terms, well, not one last thing, a couple of last things. But in terms of as we're thinking about, how do we think about how do we interpret if we've gone through and we've powered our study, right? We did our due diligence. We went through and did best practice. We found used a meta-analysis to determine sort of the effect that we're supposed to be looking for, right? And we went through, adequately powered our studies, right? And we still failed to reject the null hypotheses. What do we do with it? How do we understand this, right? Well, a couple different things. One, error in my power calculations, okay? I made a mistake somewhere, right? Always want to go back through and double check that. Two, maybe that the effect size that I'm actually looking for is smaller than what's been previously estimated, right? Maybe the studies or the research that I was pulling my target effect from, or my estimate of my target effect from, is maybe the studies that have found this overestimated the effect, and they just overestimated the effect and found a bigger effect, and that was easier for them to claim evidence for effect, and so they got published, and the ones that got a more reasonable estimate didn't. Or maybe I'm looking at this relation or this difference or this effect in a different population, and maybe it's smaller in the folks that I'm looking at relative to somebody else, right? Or maybe I'm using a different measure or something like that has impacted the magnitude of effect. So essentially, maybe my effect size is smaller. What I'm actually looking for isn't as big as what I had estimated, right? Or, and this one is probably most likely the case, or maybe I'm just a victim of a type 2 error, right? Maybe I did everything right. My estimate of my power was right. I powered everything correct. All my calculations, but I powered it for 0.80, which means 20% of the time, I'm not going to find something even if it's there. And then I just missed out, right? I just pulled the garbage card and I didn't find what I was supposed to find, right? Now, if you've gone through and done your due diligence and you have a good idea of what that effect should be, you can say, well, maybe I just whiffed on this study and didn't find the effect that I wanted to, right? But is there any way to tell that for certain based on the data that I have sitting in front of me? Nope, right? And so what it starts to become important is having your prep and calculations and justifications for the effect that you're using and things like that done beforehand so that you can help sort of make some sense of this if you do fail to reject, okay? Last thing in terms of power stuff we want to talk about is something that a lot of, like SPSS will give you this idea of observed power, okay? Now, as we talked about, if we're doing power calculations are best conducted if I'm looking for planning for some future study. All of these power calculations should be done before you measure a single score from anybody, okay? But what you'll see some people do is start to go through and use power to start to explain generally the absence of effects in observed data that they've already collected. And this is called observed power, okay? And investigators, statistical programs like SPSS will go through and you can request a measure of observed power of a test statistic based on sort of what I've run. So if I go through in SPSS, if I'm running a independent sample t-test, I can go through in the settings and I want an estimate of observed power, right? And the idea is what I can do then is if I go through and let's say Rachel's running a t-test, goes through and finds that a group with a history of self-harm we're not finding evidence that they're different from people without self-harm on some measure of negative affectivity or something like that, right? And what Rachel wants to do is she wants to get this observed power to say, well, if I find that my test has low observed power, then if I don't find an effect, I can just say that, well, it is due to poor power. Or maybe what I do, if I don't find an effect and I find that that my test has adequate power, I can say that there is no effect there, that these two things aren't actually different. Okay. Problem is that our observed power that we would get from data that we've already collected is a direct function of our p-value. Okay. And what we're going to find, no matter what, mathematically, anytime we fail to reject the null hypothesis, anytime we have a large p-value, it's always going to correspond to low power, right? There's not a situation where I can find a large p-value or obtain a large p-value and my observed power is going to be high. It's never going to happen. Anytime I get a high p-value, my observed power is always going to be low. And as a function, calculation of observed power adds absolutely nothing to anything that I could say or that would be meaningful. It's just basically a restatement of my p-value. Okay. Article that I have assigned here, the Honig and Heisey paper, referring to this as power paradox, right? What I want to do is if I fail to reject, what I want to do is if I fail to reject in a case where my observed power is high, then I can say, well, there really is no effect here because with this sample, I should have found something. So my power is high for this test, but I still fail to reject the null. And so therefore, I've got a near null effect. Problem is, anytime you calculate power from observed data, and you've got a high p-value, your observed power is always going to be low, right? And so it just functionally doesn't add anything to it, right? Now I can say, if I've got 10 people in one sample and 12 in the other, and I don't find anything, I can say, well, it's probably because I have low power. Well, it's probably true, right? But actually calculating this estimate, it seems like something that's official, right? My observed power really doesn't provide any useful information in terms of interpreting or what I'm doing with my test. Okay. And so there's arguments about thinking about the value of power analyses versus just our general confidence intervals, right? If I'm looking at my confidence interval, remember we think about confidence intervals as values that are non-refuted, values that are plausible given the data that I've collected, right? I know that my point estimate is never going to be exactly identical to the population parameter, but this confidence interval gives me values for whatever I'm estimating that would be reasonable given the data that I've collected, okay? And if I have a situation where my non-refuted values, right, or my plausible values are clustered tightly around that null effect, right, I can start to make a good argument that so whatever effect I do have is probably near null, right? If I've got a really tight, if I'm saying that if my null value, if I have the mean value under my null is, let's say, 25, and I run my test and I find that plausible values for the target population based on data I've collected run somewhere from 24 to 26, I can probably say, this looks pretty tight. And so I don't know, even if these data even if there is a difference, it's not going to be far enough off of that null value to make any big impact. And so if we've got a tight confidence interval that centers around a null value, I can start to make conclusions about that the true population parameter, if it's not the null value, it's something that's very close, right? But what ends up happening more often than not in our studies is our non-refuted values range really widely around our null, right? Because we generally have small samples, our confidence intervals are quite wide, and then what we're left with saying is that, well, reasonable estimates based on the data I've collected are anywhere from way far below my null value to way high above it. And so in that case, I really can't say much of anything about anything. All I can say is that my data or my test is not terribly precise and it doesn't tell me much meaningful about whatever phenomena I'm interested in. Okay. So again, if I've gone through and done a good job of calculated confidence intervals or thinking about these carefully, so this idea of observed power sort of doesn't really sort of contribute to much to anything. I can say, well, so these are expected values for whatever I'm trying to estimate given the null. My point estimate, still my best guess. Anything in here seems to be reasonable, right? But then if I go through and start saying, oh, well, what if my effect is, so if I say, so the difference in my, so I'm doing my two-group test, right? And I'm saying, oh, well, group A is either sort of based on the data I've collected, group A is either 2 points below or 10 points above sort of the other group, somewhere in that range, right? And say, oh, well, what if it's 15 points above? Like, I don't know, what if I could fly? I don't know, lots of what ifs, right? That's not a value that's supported by my data, right? I could say, well, sort of based on my data I've collected say it could be as high as 15 points, right? So I could say, well, maybe about 15 points higher, but that's not as good as an effect or a good of estimate as sort of what my point estimate is. It also says it could be 2 points below, right? So we start to get this idea of observed power and sort of what my power would have been if I would have been on the high end of the spectrum starts to become less important and less meaningful. It seems like it should contribute to something, but really it's not. Okay. So again, in this paper, and it's a good paper, I want you to make sure that you're going through and reading this carefully, bringing us back to this idea that the focus of our good analysis should be to start to try and identify values that are going to be supported by the data, which ones that are supported, which ones that aren't supported. Okay, and then when we're talking about power analyses, this can start to get tricky, right? Because maybe I go through and I look at a forest plot of a meta-analysis, right? And I've got all these studies that say my effect size for whatever I'm looking at should be around here. Then I've got one study, Garcia et al. Is way out here, right? And so maybe I'm like, oh, I'm going to power my study for Garcia et al. Well, Garcia et al.'s way the hell out here, and doesn't seem to be representative of all the other stuff that we can do. I can do that. Right? And it's going to tell me that I only need, say, 30 people in each group or something, and I can feel good about that, but probably what I've done is wildly overestimated the effect that I'm looking for, and at the end of the day, I'm not doing myself any favors with that. Okay? So just wanting to think about sort of bringing it back into sort of confidence intervals and using those in ways that are meaningful and help provide context to our stuff. Okay? All right. Going to switch over here and finish up talking about confidence intervals on effect size. Okay, so we've talked about confidence intervals for mean values, confidence intervals for mean differences. We can also calculate confidence intervals around effect sizes. But confidence intervals around effect sizes start to get a little bit more tricky. There's a little more stuff that goes into it. Okay, so if I'm calculating a confidence interval around some mean value, I'm using this based on my central t-distribution. Okay, this is the t-distribution that we've been using, symmetrical around 0, right? We've got half of our values are positive, half of values in the negative, and my central t-distribution completely defined by my degrees of freedom. If I know what the degrees of freedom of my test are, that tells me exactly what family of t I'm working with here. Okay, and when we're going through and running our hypotheses tests, we're using these central t-distributions, assuming a population mean equal to 0. Okay. If I'm collecting data, and so I've gone through and the null hypothesis is correct, I'm expecting half of those t-tests to be positive, half of those t-tests to be negative, centered around 0, assuming that the null hypothesis is true. Problem is that our confidence intervals around effect sizes don't assume the null value, right? If we assume the null value, we wouldn't be doing the test anyway, right? We're assuming that the distribution that we're looking for is shifted off of that null value, right? Either above or below, okay? And what we've done, remember, if we start to have a distribution of scores that aren't centered around that null, remember this is our non-central t-distribution, okay? And what we talked about this before, we're going to get a little bit into this a little bit more, sort of some technical aspects of this. We know that our non-central t is not symmetrical and it's not centered on 0. It's out, and we start to get a skewed distribution, okay? And our non-central t's are not only determined by a couple of different factors. We need to know our degrees of freedom for our test and also that non-centrality parameter, okay? The degrees of freedom tell us kind of the family that it's going in terms of the shape. The non-centrality parameter tells me how far off of that 0 mark I'm shifting, okay? And again, what is that non-centrality parameter an index of, or what is it a measure of? Someone remember? What do we call that? The degree of shift off of 0. It's our measure of effect size, right? The larger effect, the larger off of 0 I'm shifting, right? So the distribution for my effect size is determined by sort of the magnitude of that effect as well as the degrees of freedom, okay? And so my non-centrality parameter provides sort of a metric of the difference between the true mean and the assumed mean under the null, okay? So long story short, basically what we can, and this is why calculating confidence intervals around effect size has been so difficult, is because I have to use a different distribution than our t-distribution that we use, because t-distribution assumes the null value. But if I'm looking at effect size, that effect size is going to start shifting things. It's going to be something that's not 0, which starts to shift the distribution, which means I got to use a whole new different type of scores, okay? But because our effect sizes are a linear function of our non-centrality parameter, what I can do is I can start to calculate a confidence interval around that non-centrality parameter, and then take the values of the upper and lower limit of that non-centrality parameter, convert that back into an effect size, and now I've got confidence in upper or lower bound for whatever estimate it is that I'm actually trying to target here. So, and again, from that Wilkinson article, talking about interval estimates should be given for any effect size involves principal outcomes. So not only should we be trying to give some measure of the magnitude of effect, but also wanting to give some estimate of the precision of that point estimate of effect size. Okay. So these non-central t distributions. We know that our non-central t is centered at the non-centrality parameter, right? And the non-centrality parameter is that shift off of 0. Okay. Non-centrality parameters can take on any value from positive to negative infinity. Okay. With our non-centrality parameter at 0, we've basically just got our central t distribution. Okay. But what we know about these non-central distributions show a considerable level of skew, particularly at low degrees of freedom. If we don't have a lot of people in our samples, we start to get very, very skewed distributions. And this skew starts to increase the farther and farther we get off of that central t distribution. Okay. So if we take a look here, we see that with 60 degrees of freedom, this is going to be our central t distribution. But as our non-centrality parameter goes from 2 to 5 to 10, with 60 degrees of freedom, we start to see a little bit more of a skew, but it's not too bad. With 5 degrees of freedom, as we start to get more and more a bigger and bigger effect with low degrees of freedom, that distribution starts to get very skewed. Okay, and so for a given non-centrality parameter, this non-central t starts to approach a central t as the number of degrees of freedom increase. So if we can see even for delta equals 10, right? As we go from 5 to 20 to 60 degrees of freedom, this non-centrality distribution of delta 10 starts to get more and more normal, but it's a very gradual approach, and even with a small non-centrality parameter, still get still maintain some level of skew, even if I have a large number of degrees of freedom. So think about taking our t distributions that we know and love that we've been working with, but as soon as that we start pulling it off of 0, we start to get a skewed distribution, and that non-central t is determined, the shape of that non-central t is determined by the degrees of freedom and that non-centrality parameter, okay, or the magnitude of effect that we're seeing in the population. Questions on this? Okay. Other thing that we're going to see when we start to calculate confidence intervals, right? Again, the idea is what we can go, because our non-centrality parameter has a direct relation with our effect size. What we're going to do is we're going to calculate upper and lower limits for our non-centrality parameter, and then back translate that into upper and lower limits of our effect size. But if we've got a skewed distribution, right, relative to when we're calculating confidence intervals around our mean values, right, we've got, so whatever our point estimate is, plus or minus my margin of error, right? And so I've got a nice symmetrical confidence bound. With a skewed distribution, am I going to get a symmetrical confidence bound? My upper limit or my lower limit is going to be farther stretched out than the other end, and so we're going to get a point estimate that doesn't fall directly in the middle of that confidence bound, and the degree of that skew is going to start to depend on the value or the magnitude of the effect size, as well as the degrees of freedom of the test. So, to this point, until relatively recently, calculating confidence intervals around effect size was very, very difficult. Because computing confidence bounds around your non-centrality parameter is fairly complex, right? There's just not tables available to go through and do these for most situations that we would run into. And so what we would have to do is we would use tables extrapolated from central t distributions, and it was a mess, it wasn't accurate, and it was just problematic. What we've got now is some calculators and some different tools that start to sort of do this for us, so that we don't have to go into, the first time I did this, I was in the middle of R, sort of manually adjusting values to try and get on a specific non-centrality parameter. Now, James Steiger, sort of big sort of guy in statistics, has this non-centrality calculator that you can download using this link. Easy peasy here. All you do is you choose the distribution that you're working with. Here we're working with a t-distribution. Go through, enter the test statistic for whatever test that you've run. Enter your degrees of freedom. Indicate that you want a 95% confidence bound for our effect sizes. Here we're using D-measure statistics. And then you just hit compute, and it'll give you a lower bound for your non-centrality parameter. Delta is just your non-centrality parameter, and an upper bound for your non-centrality parameter. Okay. This is super helpful. Again, what I've got here, there it is. All right, it's a little guy here. If I'm going to calculate a confidence interval around an effect size, and then let's say it's a D value, I'm going to hit T here. And I'm going to say I want a 95% confidence bound. Let's say I've got a test statistic of T value 2.5 with 50 degrees of freedom. Hit compute. Gives me the lower and upper bound of my non-centrality parameter. And then what I can do is I can just take those upper and lower limits of my non-centrality parameter, because non-centrality parameters are directly associated or directly linked to effect size. Back translate those into upper lower limit of effect size, and I've got my situation covered. Okay, this thing right here is clutch. Now, show of hands, how many Apple users do I have here? Okay, well, this doesn't work with Apple. So you're going to have to sort of use a PC to get sort of on this, or I don't know, talk with one of the other people who've used Macs. They'll tell you, I don't know. They'll tell you how to. CJ, do you use a Mac?
Yes, sir.
You do? All right. I was hoping you were going to say no, and then I was going to say that's why you're my GA, and it was going to be a funny joke. You ruined it.
I'm a Mac user as your
Okay, that's gross. I'm going to have to rethink that. How do you go? What workaround did you find for that non-centrality parameter or calculator?
Yeah, so Macs kind of suck for that. So
No, that's not true. The Mac can do anything PC can do. I've been told that 1,000 times. It's also more intuitive and easier.
So I did this at school.
Okay.
So I'm not exactly sure to do it on a Mac. I guess you'd have to do the thing where you log in through the desktop or whatever.
Okay. Or talk with one of your cohort members who has a real computer, and they'll help you out with that. But just so you know, if you have a Mac, you're going to have problems with this, but it's a slick calculator if you're not a Mac user. So,
Josh, can you text from your laptop?
What's that?
Can you text from your laptop?
Why in God's name would I text from my laptop?
That's exactly what someone who can't.
Like, you know what? I'm sitting down trying to work on things, not screw around. Check my sort of Instagram or sort of whatever is going on. There you'd be like, hey, don't want you do work instead of screwing around on TikTok. All right. Quick here to finish this out. Calculation of confidence intervals on effect size. So single mean, right? If we got a single sample test, all you need to do is calculate your effect size. And then lower limit is going to be your lower limit on your non-centrality parameter over the square root of your sample size. Upper limit of your effect size, non-centrality parameter over the square root of your square root of your sample size. Square root of your sample size gives you the upper lower bounds. Super easy. Okay. For an independent means, right? So independent sample t-test, we're just going to take our non-centrality parameter, multiply that by the square root of 1 over sample size 1, 1 over sample size 2. Same thing on our upper, right? Just going to give me my upper and lower bounds on this, and we're good to go. Okay. Or you can use Stata. It'll do it automatically. So theta users are able to go through and sort of get those already. Repeated measures designs, this starts to get a little bit tricky. Again, the process is the same thing as our single sample t-test, because a paired sample t-test is just a single sample t-test looking at the mean and standard deviation of the difference scores. The only thing that we need to remember here, and this is something I had to go through and dig, in order to make this work, because our upper and lower estimates for our non-centrality parameters is derived directly from my t-statistic, right? So if I'm going through and I'm inserting my t-statistic to get my upper and lower bounds for my non-centrality parameter, the standardizer that I'm using for my single sample test, my independent sample test, my repeated measures test needs to be the same standard deviation estimate that's going into the calculation of my t. Okay, and remember that the variability or the standard deviation estimate that's going into the calculation of my test statistic or my repeated sample t is standard deviation of the difference scores. Now we talked about standard deviation of the difference scores potentially inflating your effect size, because the standard deviation of the difference scores might be considerably smaller than variability at time 1 and variability at time 2. But if you go through and calculate a point estimate of your effect size for your paired sample t using like this pooled standard or the average standard deviation, oftentimes what you're going to get is a point estimate that doesn't fall within your confidence bounds, which just means that you've used that the effect or the metric that you've calculated the confidence intervals for isn't the same metric that you calculated for your point estimate, so you just have to make that match up. Okay, so when you're going in, and if you want to, there's a lot of different metrics that you can use for there are different metrics that we can select in terms of our point estimate of effect size for our independent sample means and our repeated independent sample test and our repeated measure test. But if I want to calculate confidence intervals around that effect size, that starts to force my hand into using a specific standardizer. Okay, so technically for our independent sample test, the pooled variance, the square root of the pooled variance estimate needs to be what I use for my standardizer. Essentially, my hedge is G here, right? Now, if I use Glass's delta, you probably won't be able to make it. Your point estimate is still going to fall within those bounds. But for your repeated measures, if you want to calculate a confidence interval around your effect size for repeated measures, your options are reduced to 1, and that's just taking your mean difference over the standard deviation of the difference scores. Otherwise, your point estimate's going to not fall in within your confidence bounds, and that's obviously problematic. Okay, so
Can
just
I ask you a question? Sorry.
yeah.
Yeah. So I understand what you're talking about. So for this, like, non-centrality parameter lower, is that what we get from what we calculated in this chart thing?
Nope, that's what you're getting here. So this is your lower bound for your confidence, and then your upper bound.
Yeah. Is that what we plug into there?
Yep.
Okay.
Yep.
That makes sense.
Yep. Okay. So, but to get the upper and lower bounds, same thing as our single sample test, because our paired sample test is just a single sample test on the mean of the difference scores and the standard deviation of the difference scores. So what we can also do, if you want to get gangster with this, right, what you could do is you could go through and calculate confidence intervals around an effect size, and then use that upper and lower limit of the effect size to give you a range of sample sizes needed to achieve adequate power for a given study. Okay, so what you could say is, based on this study, right, based on sort of Riley's study, Riley's got a study out here that gives me an effect size of 0.5, right? But I'm not actually sure that 0.5 is really exactly accurate. But what I could do is I could take Riley's effect size, calculate a upper and lower limit for that, and let's say it goes from 0.4 to 0.6. What I could do is I could run power analyses, assuming an effect size of 0.4, and it says I'm going to need this many people. And I could run a power analysis on the effect size on the high end and say this many people. And so starting to give me a sense for sort of what type of sample I could need in order to adequately power my test for something. Okay. And again, a lot of times this is going to give you wildly different estimates, right? Like, oh, I need anywhere from 40 to 260 people, which can be sort of maybe not terribly useful outside of just recognizing so that there's just a lot of unknowns in terms of what's going on. I would rather know, sort of walking into something, that there's a lot of variability than opposed to putting all my eggs in one basket, they get my heart broken when everything kind of falls apart, right? Because then at least I know back, well, I got as many people as I could, right? But recognizing on the front end that I need to temper my expectations, because really on the high end, I could need sort of double the sample in order to adequately power this. This is what I've chose to do, but at least I know what's going on. I know this situation walking into this. Okay. So here is just, so these next two examples, oh yeah, we'll just do this. These next two examples are just stuff that I've pulled out of, like, so I've written a couple of different papers where I've calculated confidence intervals around effect sizes and then presented those in a sort of way that I've tried to sort of use to include interpretations that are sort of kind of meaningful in terms of kind of what's going on here. So just go through and take a look. So these are just two different studies where I went through and included differences, 95% confidence intervals around the mean. Here's my test statistic. Here's my effect size, and then the confidence intervals around effect size and kind of how I wrote that up. Same thing for a different study, same type of thing, right? And so just to kind of give you examples for sort of what this might look like in an applied setting, and these are things I managed to get published, so at least someone thought they were okay. Just as trying to get a headspace for how to tie all this stuff together into stuff that we've been doing before, right? So, and that's it. Got some references there. So that's that. Questions on any of this? Okay. How about this? Technically, we would say because we've got finished this stuff, we got problem set 5 that's working on sort of talking about effect sizes and going through and calculating stuff here. Technically, that would be due on the 6th, but that would put sort of back-to-back problem sets together, where it'll take us a while to get through ANOVA. Would you like to push problem set 5, the due date for problem set 5, back to the 13th? Or is it easier just to have that sort of set up to, okay, we got strong opinions in the bottom left. But I don't know. Sometimes I feel trapped by this. I sort of say, like, oh, we're going to be sort of a little bit flexible, but then people sort of screws with people's schedules. How about this? Let's do this. We'll say that we'll push back problem set 5, the due date, for the 13th. So just give you a little bit of a breather so you're not have to do stuff back to back. That said, I would strongly recommend you to get started on this stuff earlier rather than later. This stuff is kind of tricky to wrap your head around. And if you want to, you can always turn this stuff in earlier if you want. But just to give you a little bit of breathing room between a big set and then sort of your next one. People okay with making the official deadline on the 16th or on the 13th? Okay, cool. Awesome. Well, we'll do that. Keep trucking along on this problem set 4. Let CJRI know if running any hiccups on this stuff. Otherwise, good luck, and we'll catch you all next week. Okay? All right. We'll see you, folks.